All right, let's take a look at the electron configurations for the D block. These have some little oddities to them. The first oddity that you'll see is that our N values are actually one less than what you would think it'd be. So for example, this is the 4s. When we get to the with the D block, it's 3D, and then it goes back to 4p. So the D block is always N minus 1, right? Whatever row you're on, you subtract 1 from it. So for example, 5s, 5p, in the middle is only 4D. So let's take a look at some transition metals and go ahead and write out their electron configurations. So first up, we've got manganese that we'll do. So we can tell that it has a whole bunch of core electrons that we're not really too worried about, and it'd be a whole lot to write out. So what you can do is you can take a little bit of shortcut, and that shortcut is you pick the noble gas above it, and then brackets, you just put the identity of the noble gas. So argon is above manganese, so we put argon. And what that tells the reader is it has all the same electrons as argon and then some. And then after that, we read like a book from left to right, line by line. We've got our 4s, and they're both filled, 4s2. And now we're in this one right here. Remember, it's n minus 1, so this is just 3d. And then if we count the number of electrons, 1, 2, 3, 4, 5. So 3d5. Let's do iodine as another example. So again, we can put the noble gas above it. In this case, the noble gas above is krypton. So we're saying it has all the same electrons as krypton. After that, we'll have the 5s2. Then this will be n minus 1. All 10 of them are filled. So that's 4d10. And then we've got 5 electrons here. So that'll be, again, back to our 5 level. Now we're in the p block, 5p, and then 5 electrons, 5p5. All right, there's one more weird rule with our transition metals. And this weird rule says that half-filled shells are energetically favorable. And so if we think about chromium, let's go ahead and think about what we want the electron configuration of chromium to be. So we have chromium right here. So again, the noble gas above it is argon. So we can say argon. And then after that, 4s2. And then we have 3d1, 2, 3, 4. 3d4. If we think about our d orbitals, there's 1, 2, 3, 4, 5 of them. And so fill out 1, 2, 3, 4. If we had one more electron, it would become half filled. And same thing for the 4s orbital. If we got rid of one electron, it would also be half filled. So what happens is we move this electron over here, and instead of being 4s2, 3d4, it is 4s1, 3d5, right? So this electron gets moved over to there, and then we have 2 half-filled sets of orbitals. So this is also true for molybdenum and whatnot. And again, you can check out your periodictable.com. So here's ptable.com. You click on electrons. And then if we look at chromium, right, you can tell it only has one 4s electron, and then it has all the 3d orbitals are half filled. Go down to molybdenum, the same thing, right? That electron hops over. So that occurs there. It also occurs over here for copper, silver, and gold. So the noble gas above copper is argon. And then you'd think it'd be 4s2, 3d9. But it's not, because we can make that 4s shell half filled and the other d shell completely filled. So instead it is 4s1, 3d10. So when you have 4 d electrons or 9 d electrons, one of the s electrons will jump into the d shell. So that's just something you have to memorize. Of course, if you don't believe me, you can check out ptable.com. All right, let's check out one more example, this time not of a transition metal, but something that comes after it. So we'll take a look at bismuth here. The noble gas above it is xenon. And then after that, we've got our 6s2. And then if we think about what comes after that, if we think about what the periodic table really looks like, so I'm going to zoom out here and I'm going to press this wide button. What the periodic table really looks like is this F block is actually inserted right into that position. So if you want to take a kind of look at the quote unquote real periodic table, it looks this wide, right? We don't normally draw it like this because most of our chemistry doesn't occur with these F block elements, so they're not too important, and then it makes it, a bit unreadable. So the way this goes is it goes from the 6s down to the F block. And then the F block, similar to how the D block is n-1, the F block is n-2. So this case, it'd go all the way here. Instead of being 6F, it's only 4F, right? So n-2. All of them are filled. There's 7 orbitals. That's 14 electrons. So 4F14. After that, it comes back and gets these d electrons. So then that'll be 5d10, right? n-1. And then we get the bismuth electrons. So 1, 2, 3. Those are the p electrons. So that'll be 6p3. So again, reading the periodic table left to right, line by line, there's just some little exceptions and oddities that you need to know about.